Hello and welcome. In this video, we'll be exploring the concepts of variance and standard deviation for discrete random variables. These measures are crucial for understanding the spread or variability of a probability distribution, which is a key component of the IB mathematics, analysis and approaches higher-level curriculum. By the end of this session, you will be able to define variance and standard deviation, calculate these values using two different formulas, and interpret what these measures tell us about a random variable's distribution. We'll also see how they are applied in solving problems. First, let's establish our learning objectives. You will learn to calculate and interpret the variance and standard deviation of discrete random variables. This will allow you to describe the spread of a probability distribution. Before we dive into calculations, let's understand why we need these measures. The expected value, or mean, m, tells us the average outcome of a random experiment over the long run. For a fair six-sided die, for example, the expected value is 3.5. This means that if we roll the die many times, the average of our results will be close to 3.5. However, this number alone doesn't tell us how much the individual outcomes typically deviate from that average. For that, we need measures of spread. This is where variance and standard deviation come in. They quantify the variability or dispersion of the data. Variance is a measure of the squared deviation from the mean. We denote the variance with sigma squared. Its formula is the sum of the squared differences between each possible outcome xi and the mean mu, multiplied by the probability pi of that outcome. In other words, we're calculating a weighted average of the squared deviations. The higher the variance, the more spread out the distribution is. The standard deviation, sigma, is simply the square root of the variance. It's often preferred because it's in the same units as the original random variable, making it easier to interpret. The standard deviation gives us a typical deviation from the mean. A larger standard deviation indicates that the outcomes are typically further from the mean, while a smaller standard deviation suggests that outcomes are clustered more tightly around the mean. Let's work through an example to see how to apply the variance formula. Consider a discrete random variable x with the following probability distribution. The random variable x can take the values 0, 1, and 2, with probabilities 0.3, 0.5, and 0.2, respectively. Our goal is to find the variance of this distribution. The first step is always to calculate the expected value, or mean, mu, as we need it for the variance formula. The mean is the sum of each outcome multiplied by its probability. So we have 0 times 0.3 plus 1 times 0.5 plus 2 times 0.2. This gives us a mean of 0.9. So on average, we expect the outcome to be 0.9. Now we can find the variance using the formula sigma squared equals the sum of xi minus mu squared times p pi. We apply the formula for each possible outcome. For x and 0, we have 0 minus 0.9 squared times 0.3. For x01, it's 1 minus 0.9 squared times 0.5. And for x02, it's 2 minus 0.9 squared times 0.2. Let's simplify. This becomes 0.81 times 0.3 plus 0.01 times 0.5 plus 1.21 times 0.2. Calculating these products and summing them, we get 0.243 plus 0.005 plus 0.242, which results in a variance of 0.49. This number represents the average squared deviation from the mean. Now that we have the variance, we can easily find the standard deviation, which gives us a more intuitive measure of spread. The standard deviation, sigma, is the square root of the variance, sigma squared. In our example, we found the variance to be 0.49. So the standard deviation is the square root of 0.49. This gives us a standard deviation of 0.7. So how do we interpret this? A standard deviation of 0.7 tells us that the outcomes of the random variable x typically lie within 0.7 units of the mean, which was 0.9. This means most of our outcomes would fall between 0.2 and 1.6. To recap, we calculated the standard deviation by taking the square root of the variance we found in the previous step. The standard deviation, sigma, of 0.7 indicates the typical distance of a data point from the mean of 0.9, giving us a clear picture of the distribution's spread. Sometimes, Calculating the variance using the first formula can be quite tedious, especially if the mean is a non-terminating decimal. Thankfully, there's a more convenient alternative formula. The alternative formula for variance states that sigma squared equals the expected value of x squared minus the mean mu squared. This formula can be derived algebraically from the original definition. The term EX squared is calculated similarly to the mean, but instead of multiplying each outcome by its probability, you multiply the square of each outcome by its probability. Let's recalculate the variance for our previous example to see this formula in action. Our example had x values 0, 1, 2, with probabilities 0.3, 0.5, 0.2, and we found the mean mu to be 0.9. First, let's find EX squared. We take the square of each xi, multiply by its pi, and sum them up. This is 0 squared times 0.3 plus 1 squared times 0.5 plus 2 squared times 0.2. This calculation gives us 0 plus 0.5 plus 0.8, which equals 1.3. Now we can use the alternative formula for variance. Sigma squared is EX squared minus mu squared. That's 1.3 minus our mean of 0.9 squared. So we have 1.3 minus 0.81, which equals 0.49. As you can see, this is the exact same result we got using the first formula, and it was arguably much quicker to calculate. This demonstrates how both formulas lead to the same correct variance. Now let's apply these concepts to a classic problem: finding the variance and standard deviation of the score when rolling a fair six-sided die. We'll define x as the outcome of a single roll. We want to find its variance and standard deviation. First, we construct the probability distribution. Since the die is fair, each outcome from 1 to 6 has an equal probability of occurring. The probability of rolling any specific number is 1/6. Next, we calculate the mean mu. The mean is the sum of each outcome times its probability. This is 1 times 1/6 plus 2 times 1/6, and so on, up to 6 times 1/6. We can factor out the 1/6, leaving us with the sum of the integers from 1 to 6, which is 21. So the mean is 21 over 6, or 3.5. Now, we'll use the alternative formula for variance, as it's more efficient here. First, we find EX squared. This is the sum of the squared outcomes, each multiplied by its probability of 1/6. Again, we factor out 1/6. The sum of the squares from 1 to 6 is 91. So EX squared is 91 over 6, or approximately 15/1. Now we can find the variance. It's EX squared minus mu squared. That's 91 over 6 minus 3.5 squared, which is 12.25. Performing the subtraction gives us a variance of approximately 2.917. Finally, the standard deviation is the square root of the variance. The square root of 35 to 12 is approximately 1.708. This means a typical die roll deviates from the mean of 3.5 by about 1.708. To quickly check this with a calculator, you can enter the outcomes, a 1 to 6, into one list and the probabilities, 1 to 6 each, into another, and then use the one-variable statistics function. You should find a standard deviation of about 1.708. Now let's tackle a more complex IB-style problem involving a discrete random variable with an unknown probability. We'll need to find the unknown value first, and then calculate the mean and standard deviation. Here we have a discrete random variable x. Its possible values are 2, 4, 10, and 20. Their corresponding probabilities are k, 0.05, 0.35, and 3k. Our task is to find the value of k, the mean mu, and the standard deviation sigma. The fundamental rule of probability is our starting point. The sum of all probabilities in a distribution must equal 1. So we can set up an equation by adding all the given probabilities and setting the sum equal to 1. This gives us k plus 0.05 plus 0.35 plus 3k equals 1. Combining the like terms, we get 4k plus 0.40 equals 1. Subtracting 0.40 from both sides gives 4k equals 0.60. Dividing by 4, we find that k equals 0.15. This solves part A of the problem. Now for part B, we'll find the mean mu. The mean is the sum of each outcome times its probability. So we have 2 times k, which is 2 times 0.15, plus 4 times 0.05, plus 10 times 0.35, plus 20 times 3k, which is 20 times 3 times 0.1. Calculating these values gives us 0.30 plus 0.20 plus 3.5 plus 90. Adding these together, we find that the mean mu is 13.0. This answers part B. Finally, for part C, we find the standard deviation sigma. We'll use the alternative variance formula to make the calculation efficient. First, we find EX squared. This is 2 squared times 0.15, plus 4 squared times 0.05, plus 10 squared times 0.35, plus 20 squared times 0.4. This gives us 0.60 plus 0.88 plus 35 plus 180, which sums to 21640. Now we can find the standard deviation. It's the square root of EX squared minus mu squared, which is 216.40 minus 13.0 squared. This simplifies to the square root of 216.40 minus 169, which is the square root of 47.4. Calculating the square root, we get a standard deviation of approximately 6.88. This is the final part of our problem. By breaking the problem down, we first solved for the unknown probability k, then used that to find the mean mu, and finally applied the alternative variance formula to calculate the standard deviation sigma. Let's summarize what we've learned. We've introduced variance and standard deviation as measures of the spread of a discrete probability distribution. The variance, sigma squared, quantifies the average squared deviation from the mean, while the standard deviation, sigma, gives the typical or characteristic deviation in the original units of the data. We learned 2 formulas for variance. The first is sigma squared equals the sum of the squared deviations from the mean, weighted by probability. The second, more efficient formula is sigma squared equals the expected value of x squared minus the mean squared. Understanding these measures is essential for the IBAAHL course, as they provide a deeper insight into the behavior of random variables and are used in many other statistical concepts. So, we have successfully met our learning objectives. You now have the tools to calculate and interpret the variance and standard deviation of discrete random variables. Now for some practice. Here are 5 IB-style questions for you to work through on your own. Remember to show your working and use technology to check your answers. Question 1 asks you to find the mean, variance, and standard deviation for a given probability distribution. The outcomes are 1, 2, and 3, with probabilities 0.3, 0.4, and 0.3. Pause the video now to solve it. Welcome back. Let's look at the solution to question 1. First, we find the mean mu, which is 2. Then, using the alternative formula, we calculate EX squared as 4.8. This gives us a variance of 0.8 and a standard deviation of approximately 0.894. Great work if you got that right. Now for the next question. Question 2 introduces 2 players, Michelle and Amanda, and their probability distributions for the number of aces served per set. Part A asks you to show they are expected to serve the same average number of aces. Part B asks you to calculate their variances and standard deviations. This is a common IB question type. Let's review the solution for Michelle and Amanda. For Part A, you calculate the mean for both players. Using mu equals the sum of xi times pi, you'll find that both Michelle and Amanda have an expected value of exactly 2. This shows they are expected to serve 2 aces per set. For Part B, we calculate the variances using the alternative formula. The variance for Michelle is approximately 0.70. The variance for Amanda is 1.0. Taking the square root, we find Michelle's standard deviation is about 0.84, and Amanda's is exactly 1.0. Since Amanda's standard deviation, 1.0, is greater than Michelle's, 0.84, we can conclude that Amanda's number of aces per set has greater variation, or is more spread out. Well done if you arrived at this conclusion. Let's move on to the third practice problem. Question 3 is another classic. You are given a discrete random variable with an unknown probability, k. Your tasks are to first find k, then find the mode of the distribution, and finally, calculate the mean mu and standard deviation sigma. This tests all the skills we've covered. Let's check your solution for question 3. This is actually a repeat of the extended example we worked through earlier. So you should have already seen the steps. First, for part A, you find k by setting the sum of probabilities to 1, giving k equals 0.15. For part B, the mode is the value with the highest probability, which is 10 with a probability of 0.35. For part C, the mean mu is 13.0. And finally, for part D, the standard deviation sigma is approximately 6.888. If you followed the steps correctly, this was a great review. On to the next problem. Question 4 presents a scenario about crayfish exports. Let X be the number of deaths per dozen crayfish. You're given a partial probability distribution with an unknown value k. You need to find k, the mean number of deaths, and the standard deviation of the distribution. Notice that the last outcome is greater than 5, with a probability of 0, which is useful to know. Let's check the solution to question 4. For part A, you find k by summing the known probabilities and subtracting from 1. This gives k equals 0.03. For part B, the mean mu is found to be 0.61. For part C, you calculate x squared as 1.45, leading to a variance of approximately 1.071 and a standard deviation of approximately 1.35. Finally, let's explore a problem that requires critical thinking about expected value to develop a strategy. This problem is about the game Greedy Pigs. In each turn, you roll a die. Accumulate points equal to the number rolled. After each roll, you can either bank your current score for that turn or roll again. However, if you roll a 1, you lose all points accumulated in that turn and your turn is over. The goal is to find a strategy that maximizes your score in the long term using expected value. This final problem for Greedy Pigs uses expected value to find the optimal strategy. The key is to calculate the expected gain or loss if you roll one more time. Let's say you've already accumulated 10 points. If you roll again, you'll roll a 1, 2, 3, 4, 5, or 6, each with probability 1/6. A roll of 1 results in a loss of 10 points. Any other roll results in a gain of the number rolled. To find the expected value of rolling one more time, we sum the possible point changes multiplied by their probabilities. This is 1/6 times 10 plus 1/6 times 2 and so on. Factoring out 1/6, we get 1/6 times the sum, 10 plus 2 plus 3 plus 4 plus 5 plus 6, which is 10. So the expected gain from rolling one more time is 10/6, which is approximately 1.67. Since the expected value is positive, it is beneficial on average to roll again when your current score is 10. You are expected to add 1.67 points to your score. Now the problem asks for the lowest score at which it is not beneficial to continue rolling. This means finding the score x where the expected gain or loss is negative. The general expected gain from rolling again is 1/6 times x plus 2 plus 3 plus 4 plus 5 plus 6, which simplifies to 20 to the x over 6. We want this to be negative. We need 20 minus x divided by 6 to be less than 0. Multiplying by 6 gives 20 minus x less than 0, which means x must be greater than 20. Therefore, the lowest score at which it's no longer beneficial to roll again is 21. If your score for the turn is 21 or higher, the expected value of rolling again is negative, meaning you're more likely to lose points than gain them. The optimal strategy is to bank your points. Thank you for watching. Today, we've focused on two essential tools for understanding probability distributions: variance and standard deviation. We've defined them, explored the two primary formulas for their calculation, and applied them to a variety of IB-style problems. The ability to quantify the spread of a random variable is a fundamental skill in statistics, allowing you to move beyond simple averages to describe the full shape of a distribution. Keep practicing these concepts as they form the bedrock for many advanced topics in the IB analysis and approaches higher-level curriculum. Until next time, keep learning. This video was created by ThetaWise. For personalized online and home tutoring in IB mathematics and other subjects, visit Dart Tutors at darttutors.com. Thank you for learning with us.